what does the human brain actually see when it looks at an image? Researchers are trying to decode that directly from EEG, but it's notoriously noisy, non-stationary, and spatially coarse. Most current methods just collapse the signal into a single holistic embedding, which washes out the complementary temporal, spectral, and spatial structure of neural activity. That's why zero-shot visual decoding still struggles to generalize. A new framework changes that by explicitly modeling EEG through 3 parallel input condition views. First, temporal dynamics are captured using a selective state-space model. Instead of fixed recurrence, it uses learnable state transitions and input-dependent step sizes to adaptively track long-range, non-stationary brain signals, followed by a one-dimensional convolution to refine local patterns. Second, spectral structure is handled by an adaptive learnable wavelet decomposition. Rather than forcing rigid, task-agnostic frequency bands, the model dynamically computes sample-specific weights for a bank of low-pass and high-pass filters. This produces distinct low-frequency and high-frequency streams, which then interact through cross-frequency attention, allowing slow oscillations to absorb transient context and vice versa. Third, spatial interactions are modeled with an attention-modulated graph convolutional network. Electrodes serve as nodes in a dynamic adjacency matrix that combines a fixed global structure with trial-specific functional attention, ensuring the model learns biologically plausible connectivity rather than uniform relationships. These 3 branches are concatenated, projected into a shared latent space, and aligned with frozen clip visual embeddings using a symmetric contrastive loss. To stabilize training, they add EEG-specific regularization, repetition consistency to handle trial-level noise, and prototype contrastive learning to enforce class-level semantic structure. On the THING-SEG benchmark, this multiview approach achieves 54.8% top-1 accuracy in within-subject zero-shot classification, and 40.8% in a novel cross-session evaluation, consistently outperforming prior baselines. By treating EEG not as a flat signal, but as a structured multiview process, this work proves that explicit neural inductive biases are the key to robust brain-visual alignment. Want to dive into the exact architecture and training objectives? The full paper is linked below.